The fourth part is physical process in CHOPS production. Energy sources and stresses. In CHOPS process, a set of driving forces is responsible for the continued sand influx that generates and higher oil production rates. These mechanisms operate at different scales with different effects. The major driving forces are the following: gravitational forces that help yield and dilate the sand, natural fluid pressure gradient that cause flow and lead to entrainment of the sand in the following fluid. Foamy oil flow phenomena that help sustain the pressure and the flow rate. Liquefy and keep sand in suspension and accelerate the flow velocity to the variable through growth and expansion of gas bubbles. The gravitational energy component acts as the scale of the entire reservoir and overburden. The sand liquefaction and entrainment effect happens that the green scale will locally elevated pressure gradient plug almost unconfined sand grains from their weak and dilated substrate to incorporate them into a slurry at an intermediate scale, that of the variable region. The generation of a foam bubble phase in the moving slurry has an important effect on the gradients and thus on the suspension of sand and on the flow velocity to the weir. As the sand influx is initiated in a CHOPS weir, a cavity is generated near the variable stresses, rising from the overburden weight and pressures arising from fluid flow to the variable both act upon the walls of this cavity. In the solid reservoir rock near the walls of the cavity, the radial stress is decreased and the tangential stress is increased. This results in an increase in the shear stress and a decline in the confining stress, and both of these effects tend to bring the intact formation to condition of shear yield. This figure shows us tangential that reduce stress around the cavity, leading to shearing and dilation, causing peripheral permeability increases. Because of the confining stress is low from the lateral unloading that takes place, shearing causes in the high porosity using excess near the walls of the cavity to dilate. Any small amount of mineral cohesion that may exist in the sandstone is destroyed as the sand is deformed and remodeled by shearing. Because of dilation of the sand during shear and at low stresses, the porosity will increase from the typical initial value of 30% to much higher values, perhaps 35 to 38%. Yet it will still remain as a solid mass held together by compressive stresses and heavy frictional behavior. Nevertheless, the sand has changed dramatically from a densely packed and intact sand to a shared sand of much higher porosity. This increase in porosity has dramatic effects on the absolute and the relative permeability values, and also leads to changes in phase saturations during CHOPS. All the important properties of the oil reservoir change. 3D geophysical seismic surveys carried out by some company, notably Canada Petroleum, show this clearly. These surveys show that a CHOPS well that has produced over 100 meters of sand in its lifetime is surrounded by shaped low seismic velocity regions, wells that have produced more sand. This figure shows us low seismic velocity around CHOPS well have probably larger regions of low seismic velocity. Wells that never were successful in sand emission have no detectable zone of low seismic velocity. Also, even though extensive data remain in the public domain, it appears that the ellipticity of the zone is consistently elegant in an individual field. Seismic waves that pass through the disturbed region may also show no shear waves in the wave train. This is because the transmission of shear energy in a high porosity medium at low stresses and with some free gas and greatly impeded, and the waves may be completely altitude. Note that it is difficult to analyze the seismic wave velocity reduction in terms of three possibilities. This becomes a challenging non-unical problem in these difficult high porosities of 35 to 44% around a variable may be deduced from a geophysical behind the casing logs executed on wells that have produced a large volume of sand. These high porosities are measured only after the tubing and PC pumps that have been removed from the well and a geophysical logging unit lowered down the well. This usually takes from 4 to 10 hours after production is interrupted, so geophysical log data may not represent of conditions when the well was actively producing. After stopping production, sand has some time to settle. This figure shows us zones around a CHOPS well after some sand production. around the variable because it is not being drawn in activity. Through the perforations and the gas bubbles in solution have more time to rise upward and segregate from the foamy oil. Nevertheless, the data indicate that during production, it is likely that a liquefied zone existed near the variable. Through the size and the vertical extent of this zone is different from well to well, and borehole geophysical methods cannot probe far from the variable. Not only is there a general higher porosity in the near variable region, but after a large amount of CHOPS and influx and carbonate cemented strata can no longer be identified. They have been destroyed. Often under Earth, the cap rock, a zone of exceptional high porosity is found. This is believed to be a small gas cap in a limited volume void that can be sustained in a stable state because of the cohesion of the cap rock. In CHOPS wells is thought to arise because of episodic draining of this small gas cap. Once it grows large enough to intersect the uppermost perforations, the gas then flows out of the void until it is drained before reversion of foamy oil and sand production takes place in the well. Clearly, stress-related factors are important in the CHOPS process because the sand is yielding and dilating. It can be shown that stress must be redistributed at the reservoir scale around the well, and even at the submeter scale around any channels that may be propagating or that may have been created by a piping process. Figure 4.4 shows the conceptual effect of producing sand on reservoir scale stresses if the process is mainly by the compact disturbed zone. Note that the compact zone does not have to extend the full height of the reservoir. It may be limited to the upper part of the reservoir or to a zone that is overlain by part of the reservoir with some cohesive strength. This picture shows us geophysical log response in a CHOPS well. What happens in the reservoir? The total weight of the overlying rocks must be carried, and the downward movements that accompany this process provide energy to maintain it. The amount of work associated with this express, where the vertical stress acting across an area A provides useful works as it moves through a vertical distance. This work is unavailable to conventional production reservoir mechanisms, where the reservoir rock is usually behaving in an intact and relatively rigid manner. In order to become fully suspended in a fluid, sand must locally exceed a porosity of about 48 to 52%, at which point all forces transmitted through static green to green contacts disappear, so that stress can no longer be transmitted through the solid phase. After liquefaction, and as long as the sand grains are in suspension, only pressure exists in the slurry, and all mixture stress has disappeared. This pressure nearly the variable is a small fraction of the overburden stress, less than 1 ampere, is most CHOPS wells under aggressive drawdown. Thus, in the medium, liquefaction front must exist where sand is undergoing a transition from a solid condition to a slurry condition. This liquefaction front, whether it is relative uniform around the variable or whether it occurs in long channels with liquefied tips, defines the boundary between the classic flow zone and the liquefied zone in Figure 4.4. The lines between zones in figure and in the ground are to be understood as general, diffuse, and extensive boundaries, not sharp zones that can be delineated easily either or through monitoring. Once the sand is locally suspended or fluid in a slurry, only fluid pressure can be transmitted through the cavity. The vertical matrix stress that has been lost in the zone around the well must be redistributed outward around the well to more intact and strong rock. The solid rock or frictional green contracts exist as rock in a plastic condition or rock that has not yet been sheared and transformed into a ductile plastic stick. These issues are revisited in more detail later in this chapter. Flow enhancement mechanism. The flow enhancement observed in CHOPS were addressed mainly from 4 factors: sand flux increase, general fluid mobility, continuous sand production generators as a growing zone of high permeability around the variable solution gas behavior in form of bubbles, destabilizes sand, maintains pressure in the fluids, and accelerates flow to the variable. If sand is continually produced, the variable region cannot become blocked by the precipitant and fine-grained practical or mineral deposit. Daisy velocity increase with sand influx. If a porous medium matrix is immobile, the Daisy velocity of the fluid is taken relative to a fixed frame of reference. However, if the metric is also moving, the Daisy velocity is the difference velocity. Sand movement thus directly increasing the velocity of the fluid phases relative to the metric, which has the effect of increasing of fluid velocity for a particular pressure drop with respect to the fixed frame of reference of the observer. There are several where this effect could be substantial. In the early stage of sand influx in more viscous heavy oil reservoirs, sand content usually approaches 40 to 45% by volume of the total dead produced material. In this phase, the reservoir is almost being mined. The massive sand movement is almost entirely responsible for the early flow enhancement that is observed in CHOPS wells. However, sand flux diminishes with time and its effect gradually becomes relatively less important if the dominant sanding mechanism is advancement of piping channel. It seems like that at the advancing tip, the sand is being liquefied at almost the same rate at which the heavy oil is flowing into the channel tip. Therefore, at the local scale of piping channel tip, the sand concentration in the liquid remains high as the channels continue to propagate into the formation. As the slurry with high sand content flows toward the wellbore through the channel, it is progressively diluted by slow liquid influx from adjacent reservoir zone. This figure shows us the dilution of sand during slurry transit along a channel. The farther the tips from the wellbore, the more dilution occurs, and therefore the lower the sand cut becomes with time. The process of sanding is a continued liquefaction of the sand fabric. Because of the high viscosity of heavy oil and elevated pressure gradients where liquefaction is occurring, the velocity of the suspended sand grains is similar or somewhat less than the fluid velocity given as the pressure gradient. Here is one dimensional press drop. U is the viscosity and Kp is the measure of permeability of the sand fluid mixture. Of course, it is difficult to define precisely what the permeability is in a medium that is experiencing gradually dilation from certain percent porosity to the point of liquefaction. thus the little impedance to flow and small pressure drops arise if the solid phase is moving at the same rate and really as the fluid phase. Although it appears that this effect is negligible overall in case where sand production rates drop below a few percent, it likely remains important locally at the sites where sand is being liquefied. Permeability enhances zone development. The withdrawal of solid from the reservoir through the process of the liquefaction and the transport to the producing well creates a space within the producing horizon. This space is not void, it is a remote zone of higher porosity sand, or it is filled with slurry composed of sand, oil, water, and gas. The growth of this remote zone causes an increase in apparent permeability of the variable region. Because this zone grows with the continued sand production, the well behaves as if it has an increasing radius with time, assuming that the permeability of the remodeled and liquefied zone is much higher than that of the virgin formation. The enhancement effect may be expressed The remodeled zone is unlikely to be a uniform zone with sharp boundaries, rather than conceptual model shown in Figure 4.6 suggests in the sharp of zone of enhanced permeability. This figure shows us enhanced permeability around a variable that has produced sand. There is a nearby region filled with high porosity slurry, where the permeability is huge, but for the most part the remodeled zone is viewed as a dilated, partly remodeled region with diffuse gradational boundaries. How large is the remodeled zone radius? Assuming that on average the reservoir sand in a body dilates from 30% to 35%, and that the reservoir cap rock does not deflect downward substantially for each cubic meter of sand produced. A reservoir volume of up to 1.5 to 20 is affected. If sand is produced mainly from piping channels rather than a cylindrical zone, the affected region may be much larger. It seems reasonable to assume that after 100 to 300 meters of sand has been produced, there is a remodeled region of 1,000 to 5,000, giving a reduced rate increase of 50 to 100, depending on the thickness of the zone affected. The production enhancement factor from this effect alone should approach 4 to 5, providing other boundary conditions remain the same. Seismic velocity measurements on other fields suggest that the zone approach traces the interval spacing distance after many years. Therefore, really in excess of 100 meters have been confirmed in the field. The remote higher porosity zone may not extend over the entire vertical height of the reservoir. Logging data and other lines of evidence suggest that upper parts of the reservoirs are more prone to thinning. The remodeling and yielding process are thought to move outward and upward from the porphyric interval, giving a large effective radius that for a zone of uniform height. The remodeled zone porosity distribution is not yet well known, but near variable values of 42 to 45% have been determined. Note that 45% is close to the maximum porosity for loose sand in grain-to-grain contact under very low stress. Whatever the geometrical details of the zone around the variable in a CHOPS where the effect of continued sand production is outward propagation of a zone or channels of high permeability. So the flow capacity of the well continues to slowly rise. Foaming oil behavior in viscous oil. The third flow enhancement mechanism is related to exhaustion of dissolved gas. This is a type of solution gas drive, but there are a number of important differences from conventional solution gas behavior. The heavy oils being explored by the CHOPS have gas in solution. The bubble point usually is or near the pore pressure. Wells are subjected to aggressive drawdown, and the gas is dissolved as bubbles. However, these bubbles do not coalesce rapidly to form a continuous gas phase. They remain as bubbles during flow to the wellbore, expanding in size as the pressure declines. Hence, the bubbles act as an internal drive force, expanding and driving the slurry to the wellbore at a velocity greater than the predicted by conventional liquid flow because bubbles move with the fluid and discrete gas channels apparently do not develop in CHOPS wells. There is no direct drainage mechanism to deplete gas pressure far within the reservoir. Thus, gas oil radius remains constant, often for years, and virgin pressure may be in contact only a few hundred meters from producing wells during later in field drilling activity. Foaming oil is developed in an induction zone where bubbles nucleate in response to the pressure decline, assuming that bubble exhausts in a pore subject to a pressure gradient. It will displace to block or impede flow through the pore throat, reducing the fluid flow capacity of the porous medium and causing the local pressure gradient to rise. This helps destabilize the formation sand because it increases the hydraulic drag force on grains in a porous medium. The drag force on a single grain can be expressed as here. The body force vector F is proportional to the cross-sectional area A. The grain with W and the pressure gradient corrected by grain sharp vector S. This figure shows us the involving gas bubbles block pore throats, developing a higher pressure gradient and helping destabilize the sand. Mechanics are sketched in figure. It appears that induced body force must be coaxial with the gradient direction. At some point, like within or just downstream of the bubble induction zone, the pressure gradient becomes large enough and the restraining frictional forces small enough to permit individual sand grains to be removed from the sand mixture, a process known as liquefaction. This is the plucking of sand grains or aggressive of grains from the substrate must take place almost continually in many locations around the troposphere, regardless of the geometrical details of the inlet zone. That the trops may have applications in reservoirs with small amount of cohesion, but there are also strong physical reasons to believe that if the cohesion is substantial, the sharing will, as the zone attains a large diameter and the sand production ceases. Nevertheless, if the enhanced production in such a case arises mainly from the enhanced permeability zone, this response a possible beneficial wear management model for slightly cohesive reservoirs. Figure 4.8 shows the probable distribution of pressure around a troposphere arising from the foaming flow mechanism near the wellbore in the region of high permeability, large pore throats, and particularly liquefied material. The pressure gradient is thought to be low. Indeed, pressure measurements in wells that stopped the production many years ago show that low pressure can be sustained for several decades near a well, despite the proven existence of higher pressures in interval regions. In the bubble induction zone, the pressure gradient is steep because this figure shows the pressure distribution around the troposphere with the formal oil zone. Because the evolving bubbles block the pore through these deep local gradients are also thought to be partly responsible for the sand destabilization and liquefaction. Beyond the bubble induction zone, the reservoir pressure are almost at their virgin condition, and the pressure gradient are again low. Elimination of skin effects. The preceding three mechanisms are amenable to be mechanical analysis. Once the details of the physical process are qualified, the force factor cannot be analyzed because it is the absence rather than the presence of a process, but it is great particular importance. Heavy oil contains semi-solid materials comprised of complex organic molecules, which give airborne heavy oil its characteristic odor. These molecules aggregate with pressure decline and with gas depletion. The asphaltene aggregate block pore through, thereby degrading permeability and impairing the production rate of heavy oil wells. In the interstices of the typical heavy oil reservoirs, there are fine-grained minerals that can be mobilized under high pressure gradients and under the effect of viscous drag forces and shear distortion. These forces tend to liberate particles that are weakly bounded through electrical attention. These liberated particles migrate and accumulate at pore throats, where they form stable blockage. Finally, some formation waters are saturated with mineral species that many precipitated in the near variable environment, blocking pore throats. This is not expected to occur in the CHOPS region because the typical geochemistry is not approached, but in some high porosity sandstone oil field. Dissolved mineral precipitation is a difficult problem that imperils their productivity and necessary repeated workovers. If sand is kinetical, free to shield, dilate and undergo liquefaction as in CHOPS, then pass through blockage and build up the local pressure gradient will continually clean themselves up by sand movements and liquefaction. Furthermore, dilated sand has substantially larger pore-throughs and liberated materials are more likely to be flushed through the systems successful without generating blockage. This behavior has been confirmed in sand management approaches for high-rate oil wells. These wells over time develop more and more negative skin as blockage are cleaned up through sand bursts. Although it is not a physical correct view, a heavy oil well on CHOPS may be viewed as having a massively negative skin. Change of mechanism with time. During early production, drainage surface area is small, flow distance is short, gradients are extreme, and sand production rates are high. At this point, the effect of sand flow increasing fluid flux dominates enhancement. Foaming oil processes are already developing near the wellbore, and this add distillation, higher initial sand cuts, and gas contents in CHOPS well confirm this. After the process has produced 100 to 300 of sand, the drainage surface area is large, and larger quantities of oil can slowly ooze across interface under the local pressure gradients. Sand is destabilized locally, perhaps at channel tips where gradients are high, but the second process now begins to dominate fluid flux. Foaming oil behavior continues to help as a driving force and as a local destabilization mechanism, particularly where pressure gradients are high. GOR values remain constant, an important and very revealing fact. This behavior confirms that there is no continuous gas saturation network that is depleting the gas content of the liquid at a distance from the well. A process that is typical of conventional oil production. In the late life of CHOPS well, after about 1,000 of sand have been produced, general solution gas drive depletion gradually become important, and GOR values may now be observed to slowly climb, indicating that the particularly connected gas phase or a small gas cap has formed. Gas slugging in wells may occur in this stage, indicating gas accumulation in the near wellbore region to form small gas pockets that are episodically drained. Water influx is now more probable because of the high permeability zone that extend a great distance. The probability of the encountering mobile water is now much greater than during the early life of the well. The CHOPS process, the decade that the driving forces from solution gas depleted and disturbed remodeled zone are now large enough so that they interact between whereas the entire reservoir is not affected by the sand flux disturbance and pressure depletion. Apparently, the dominant flow enhancement mechanism evolves during the CHOPS process. However, if sanding suddenly ceases, for whatever reason, oil rates invariably drop. Sudden oil production drop likely occurs because of perforating blockage or sand compaction near the wellbore. Stable sand arcs from being the casing, creating traps from manners and blocking fluid flow almost totally. In practice, when a well suddenly ceases production without processor phase changes, workovers strategy focus largely on the reopen perforation, perturbing the formation, the reduction capillary effect so that the reason for the blockage is removed. Because of a higher density, sand particles in following slurry may be slightly retarded during flow, and there is undoubtedly a tendency for large particles to settle in the near wellbore vicinity. Larger particles will settle more rapidly, and larger particles also arch around perforation opening more effectively. This sorting may be responsible for stable producing wells or often experiencing a sharp drop in sand and oil producing rates, which can then be resolved by aggressive workover strategy. It is important to note that the actual value of the pressure and porosities in the extensive zone around CHOPS wells cannot be measured by any known means. Permeability, reservoir compressibility, and stress have all changed. and the values of these parameters can vary greatly over short distance. Since the distribution of this alert region is not known a priori, the wear test data cannot be analyzed regionally. Furthermore, no wear test model yet accounts for flow enhancement through sand flux and bubble growth. Therefore, the models that are available are physically incomplete for CHOPS process. It is also difficult to predict the evolution of reservoir parameters over time using more complex models. These models are fitted to production data history to give a prediction on future behavior, and this process supposedly improved the usefulness for the model of predicting the behavior of other wells in the reservoir. However, if the physical processes that are specified in the model do not correspond with those that actually occur, then the model must be viewed only as a fitting procedure. Using such a model to make about physical states in the reservoir cannot be justified. CHOPS processors are extremely complex and not. This figure shows us the complexity of the process around the CHOPS well. Are not fully understood at present, it remains necessary to monitor and attempt to understand the physical processes in order to optimize their behavior. Nevertheless, predictive capabilities will improve as models that are based on real physical processes are developed. Channels on compact growth zone. The two limited physical mechanisms that can be responsible for sand production and compact growth of yield. A remodeled zone as a cylindrical body. This lead to different, although the impact on wear productivity may not be quantifiably feasible through measurement. Uniform remodel zone growth concepts in compact growth sketched in figure. The ratio of the area of the fully yield and liquefied zone to the volume enclosed approach in minimum because of the link of the complex local boundary shapes may exist, and the boundary between slurry and intact rock is undoubtedly diffuse. However, for analysis, the compact zone must be nearly by a geometrical regular shape with a distinct liquefaction front. A circular 2D assumption is the simplest for analysis because the radius of the zone and the hints of pressure gradient can be scaled directly to the sand production volume with no additional assumption. Although a diffuse phase transition zone develops, it may be treated as a thin front, just as its temperature and heat flux analysis in a melting alone that does not have a sharp melting front. However, overburden stress plays a major role in the destabilizing and dilation process, and a 2D model cannot capture this process in a regional manner, so additional samples have to be made. There are strong physical arguments that support the compact growth process. The yielded and liquefied zone can support little of the overburden stress. Therefore, much of the stress must be redistributed outward from the variable region. Of course, this adds to the force that cause yield and deletion. However, the intact shear overburden does not yield and therefore cannot strain into a sharply bent shaft or one with complex curvature. It behaves like a zinc beam with high stiffness, and this smooths out and the geometry of the deformation and yield zone. Outward extension of the distributed zone will shed much of their vertical stress as they yield, so they carry less vertical stress, whereas stiffer intact zones that protrude inward must carry more stress. Thus, the stiffness of the overburden causes smoothing of deformation, leading to the continual redistribution of the stress to the yield zone. By extension of this argument to 3D, one may deduce that smoothness in deformation that is enforced by the stiffer overburden beams tend towards of yield with a compact growth zone, keeping the boundary nearly circular to elliptic, and suppressing fingering of plastic flow zone deep into the surrounding intact zone. This figure shows us the distribution of stress around a compact growth zone, and this figure shows us the zone homogeneous through local stress. Piping channel growth concepts. It is reasonable to assume that piping channels that might develop stable structures, nearly cylindrical and consistent cross-section area along their lungs. The channel is filled with slowly flowing slurry, and the tips of the channels are propagating away from the variable as sound is being produced. As the size of the effect zone is increasingly influenced by the impermeable upper and lower reservoir boundaries, the nature of the flow will evolve from a spherical pattern to one that is cylindrical, dominated by the radial growth of channels. This to reservoir drainage pattern channels as the radius of the influence increases to a value larger than the reservoir thickness. If the dominant mechanism for sound production becomes piping channel growth at some time during the history of CHOPS ware, there are two reasonable limiting cases for the nature of the channel network. At one extreme, a number of channels develop outward from variable, and the number is constant with distance. At the other extreme, channel repeatedly and 3D geometry is created where the volume density of the channels remains constant within the effect volume. These are considered to be limiting cases because it is difficult to rationalize either a decreasing number of channels with distance or an increased channel volume density within distance. This picture shows us the channel model limits. And this picture shows us the equivalent permeability in different models. It is impossible to make conclusions as to physical nature of the process in the reservoir based solely on the tests performed at the variable phase. A more direct means of observation is required but still lacking. For piping channels, there are two possible cases with respect to fluid flow and drainage of the reservoir. These are called the strong piping case and the thin length case. In the strong piping case, fluid flow is strongly channeled within the wormhole, and the tip processes and pressure gradient that drain the reservoir beyond the tip dominates solid and liquid flux. In the thin length case, individual channels serve also as drains for surrounding oil. The sanding at the tips is dominated by local gradient, but the permeable channels serve as lateral drains and dominate the overall oil production. In extremely viscous oil, mobility is extremely low, and the sand cut remains elevated for a long time. This case more closely approach the strong piping case, with much of the fluid coming from the tip region. In lower viscosity oils, the slurry is more highly diluted. This picture shows two limiting flow regimes for channel drainage. During transit to the weir, this more closely approached the permeable thin lens model. The reservoir contact area for channel growth is potentially far larger than for compact growth. Using the same figure of 500 of sand produced in the compact zone example, if channels average 30 diameter, the contractor area is 66,000 rather than 800. Even an extremely slow-moving liquid can attain suspension production rates with such a large drainage surface. Combined compact and wormhole process. Several arguments lead to the conclusions that sand producing does not occur by either mechanism alone. Assuming a mean stable channel diameters of 30, after 1,000 of sand produced from a weir, the total channel network length would exceed 100 kilometers. Stated otherwise, in a reservoir 10 sink with 20 acre well spacing, each cubic meter of formation will contain on average 10 of 30 diameter channels responding only 1.17% of the volume of the reservoir. This scenario seems improbable, but perhaps the piping channels are larger than 30 in diameter. During the early part of CHOPS production, when the remote zone is small and the sand production rate is large, it appears that compact growth is dominant. The radius of curvature of the zone is small, and the intact wall can thus sustain a high tangential stress that piping channel development. The sharper of the radius of curvature, the greater the stability of the sand face, and any perturbation of the surface will tend to heal itself, even though the local pressure gradients are high because of focusing of the flow lines. This figure shows us the focusing of flow lines near a smooth interface. Whether a perturbation will heal itself or propagate depends on the balance of all forces involved. If the rate of the energy expenditure with time is positive, the perturbation will heal. If it is negative, the perturbation will propagate, and the channel will grow. As the channel grows, the energy expenditure rate changes because of extra energy needed to sustain a 6 slurry flowing long distance through a narrow channel. If the perturbation propagates, it generates its own high permeability channel that advances into a less depleted zone of the reservoir, accessing zone where a higher pressure gradient at the tip can be maintained to maintain growth. This transition between compact and channel growth over time is not entirely speculative in the field. Communication between wells and repeatedly being observed, but mainly for metro wells, which have produced a purable amount of sand. Furthermore, analysis of sand product modes, which couple with both flows and stress, confirm that stable channel growth is favorite late in the well life, whereas compact growth is favored during the early production history of the CHOPS well. Reservoir scale stress changes, either compact or channel growth, will lead to the development of a region of the softer material that has yield and therefore is more compliant and can carry less of the overburden stress. The total overburden load must, however, still be supported in order to maintain overall stress. Therefore, the interval value rises. At the same time, the lateral stress within the reservoir drop everywhere because of the continuous sand removal. The reservoir is thin compared to its length, so stress is maintained by redistributing stress into overlying and underlying strata, just as the vertical stress are redistributed to the flanks of the cavity. This behavior follows the principle of the stress cannot be destroyed, only redistributed to other parts of the structure. Just as in a building, if one column gives way, the other columns must carry additional load. Hence, one major microscopic effort of sanding is the general lowering of in the reservoir. Attempts of inject fluids into wells that have produced large amount of sand show that the fracture gradient has dropped from initial values of 17 to 22 kPa per meter to as low as 7 to 9 kPa per meter. Nearly of the vertical stress. Note that the stress limited in the plastic zone surrounding. This figure shows us the vertical stress at the interval scale. And this figure shows us the horizontal stress at the reservoir scale. The well undoubtedly about equals 3 and the pore pressure is also low. This suggests that the lower limit is controlled by frictional plastic flow. The residue of 3 comes from soil mechanics consideration. CHOPS wells that have produced above 100 to 200 of sand cannot be maintained full of injection liquid. Continued injection will lead to undiluted fluid breakthrough in nearby producing well, indicating either open channels or the generation of the wide induced hydraulic fractures. Carefully monitor the field test suggests the flow mechanism in fracturing as the formation acceptance of the fluid ceases rather suddenly, implying fracture closure when P injection equals in channel flow, a gradual decline in pressure would expected. In a massively perturbed stress field with low fractures will propagate from the ignition point toward other zone of lowest. This leads to rapid interval communication during injection. Communication, however, does not take place with adjacent wells that have not produced sand. This behavior is an alternative explanation to the wormhole hypothesis, which, although widely believed, remains conjectural. All phenomena explained in terms of wormholes can be explained in this figure shows us the falling head flow test indicates fracturing at the low stress around a CHOPS well rather than channel flow or Darcy flow. A procedure is where was filled as rapidly as possible within water level monitored with time. Solid line behavior was observed. Channel case pipes should lead to a gradual drop, and fracture case very sudden drop, sharp corner from fracture closure once head drops below. Low fracture gradient also creates difficulties in workovers, and fluid cannot be returned to the surface in the annulus. Therefore, pump-to-surface method have to be employed of full workovers use generate surface returns. Note that the horizontal stress concentration above and below the zone lead to excellent fracture containment if fluid are too be injected at a later date. And this may be important in considering other recovery technologies. Nevertheless, as in all thermal injection projects, large-scale injection of the hot fluid will eventually result in both repressionally and restructurally, so that fracture gradient can eventually retain and even exceed the original values. Stress around a channel. A small channel in a UCSS has a stress distribution around it that is governed by a combination of fractional yield and nonlinear elastic response. Figure 4.19 shows how the effective stress around a channel in a UCSS must be distributed. Right at the wall, both the radial and tangential effective stress must be small if there is no cohesion. Cohesion has likely been destroyed by straining at the stage. A small amount of arcing may act, and there may be capillary effect because of the fractional water saturation, giving an apparent cohesion, but a few kPa at most. The stress reduction due to the cavity must be balanced by redistribution further from the opening, where the confining stress effect allows the sandstone fabric to withstand larger shear stresses. This stress distribution is similar to that around the large zone, except a small scale. One effect of the presence of channel is the general softening of a large volume around the channel, and this may also be zone of dilation and enhanced permeability. In reservoir, the presence of many channels must therefore have an overall softening effect, leading to large-scale stress redistributions between inactive reservoir zone and zone that contain channels which, at large scale, look quite similar to the compact growth model. And this figure shows us the stresses at a small scale around the channel. Okay, the CHOPS introduced by now is over, and let's see the next time.